After de Broglie, Erwin Schrödinger is the second source of basic quantum mechanical knowledge in our search for a solution of the quantum problems. His role is somewhat unfortunate in that his success overshadowed the work of de Broglie, which therefore largely got forgotten. Here we will re-establish the relation. The fact that this role fell to Schrödinger is not entirely coincidence. Einstein got knowledge of the thesis of de Broglie, with its oscillations, because he was asked for his opinion on it, which was very positive. And Einstein probably told about it to Peter Dirac, a renowned solid-state physicist, on the extreme left in this famous picture. Schrödinger worked at his Institute on Wave Equations for Phonons, the waves in a solid, and Dirac asked Schrödinger to give a lecture on de Broglie's work, and afterwards noted that it lacked a wave equation. The rest of this talk is on what followed. What Schrödinger told his colleagues exactly is lost in history, but we can assume that it included de Broglie's main results, his expressions for the frequency of the quantum mechanical oscillation and for its wavelength. Here we will show how these expressions led Schrödinger to two differential equations. The first one he didn't publish and became later known as the Klein-Gordon equation. The second is the one that became known as the Schrödinger equation and is also frequently referred to as the fundamental equation of quantum mechanics, which, as stated earlier, it is not. It cannot be the fundamental equation of quantum mechanics because it is valid only for low velocities. It is not relativistically invariant, as all physics should be. Equally popular is the phrase the Schrödinger equation is a wave equation, mostly in the shorthand of the Schrödinger wave equation, which is less conspicuous as the first one, but not true either. Here speaking to us is colleague Nick Lucid of the Silence Asylum, see the link below. In his announcement still rather careful by adding a question mark. As he points out, the truth is that the Schrödinger equation belongs to the class known as heat equations, which describe the one-time evolution towards an equilibrium. It is that way because it lacks the second-order derivative in time, the acceleration, that is needed for an oscillation, so also for a wave equation. Like his first one, that became the Klein-Gordon equation, does have. So back to that one, at which point the search started for a catchy illustration of the Klein-Gordon equation, but as for the de Broglie energy relation, this turned up nothing really suitable. What is shown here is one of the usual ways to introduce it, more or less as a postulate. This is not the way Schrödinger did it, as can be seen from the notes he made, but all accounts of it say that how he did it isn't entirely clear. But with de Broglie's work as a starting point, and using common sense, the way he got to it can be reconstructed with reasonable certainty. Start with a phase function of the familiar form, and give this phase function the properties derived by de Broglie. Now differentiate this de Broglie phase function twice to time and twice to space, as one does in the standard wave equation. This results in a single expression. Now simply replace the zero at the end of the standard wave equation by this term, and there you have it, a wave equation for de Broglie phase functions, or wave functions, the Klein-Gordon equation, or the relativistic Schrödinger equation, as it is preferably called here, but that's a matter of personal choice. The comparison of the differential equation with the mass-energy relation, used by de Broglie in the shorter form with the gamma, now also gives the formal equalities known as the Schrödinger, or quantum mechanical, or just plain operator definitions. Usually one derives the Klein-Gordon equation from the mass-energy relation through the operator definitions, but in fact the physics is the other way around. The operator definitions are also frequently used as a means to introduce quantum mechanics without referring to waves or oscillatory concepts, but that is equally incorrect. This derivation seems almost trivially easy now, But it isn't if you have to do it for the first time. There are many choices to make without knowing what the result will be. But its solutions didn't work out for atoms, so Schrödinger continued his efforts. Again, the how he did it isn't entirely clear. Feynman says of it that he grabbed it out of the air. But, again, with common sense, it can be reconstructed with reasonable certainty. So what he had at this stage was an equation for relativistic wave functions. Perhaps he realized that the states of atoms weren't fundamentally influenced by relativistic effects, but in any way, what he did is to try to get to a non-relativistic one. Here's a possible route. Use a wave function wherein space dependence or amplitude and time dependence are separated. After differentiation, the now common time-dependent part drops out, and one gets an equation for the amplitude function expressed in energies. The energy terms on the left can now be rewritten in a relativistic and a non-relativistic part. After taking the non-relativistic limit, one ends up with the kinetic energy and rest energy separated. Now treat the rest energy as a constant, rewrite the kinetic energy towards the total energy, and replace the latter with its corresponding operator. The final result is the time-dependent Schrödinger equation in the form that one finds in many of its illustrations. Conclusion: like the ones towards the relativistic equation, all of the steps towards the non-relativistic one look rather trivial once you write them down. Again, rather trivial only once you know what the right path is. The crucial one is of course the split in time and space dependence, whereby the time dependence can be removed from the relativistic energy. So now we have a physical picture of how these two crucial equations are related. The relativistic Schrödinger equation is the equation obeyed by the high-frequency de Broglie wave functions, and the non-relativistic Schrödinger equation is its corresponding low-frequency amplitude equation in the non-relativistic limit. These are things that will reappear in the solution of the quantum problems later in the series. And we may conclude that Nick Lucid was right. The non-relativistic Schrödinger equation is not a wave equation. However, this loss is offset by two gains. The wave-particle duality is now half-wave being solved. The permanent oscillation of de Broglie is now the background of the Schrödinger oscillation. And it is this Schrödinger oscillation that experiences the wave-particle duality, in that in case of a stationary particle, it disappears. Its energy gets zero, so there is no oscillation, and therefore no wave function, while the de Broglie oscillation is still there. The other gain, of course, is the fact that the non-relativistic equation indeed gives the right solutions for the atomic state, which is done by going over from translational x, y, z to rotational r, theta, phi coordinates and introducing rotational symmetries. In order to do something similar for the relativistic equation, one first has to extend it to 3 dimensions as shown, and then introduce a rotational symmetry, which is precisely what Paul Dirac did and is the subject of the next part.